I've got the pleasure of giving the opening lecture in this school. So for this lecture, I'm going to sort of stand back and give a sort of overview, perspectives of the Muon, looking at it from different angles, sort of setting the scene for the more detailed talks that will follow on. So the basic outline of my lecture, I'll start off discussing the key properties of the Muon, and then the first perspective, historically was the first perspective, it's the high energy particle physics perspective, where the context in which the Muon was discovered, and it continues to be an important part of high energy particle physics. Our main interest is stopping muons in matter and studying matter with muons, so we need to actually slow the muons down, and the slowing down process, one takes a radiation physics chemistry perspective to follow. And then perhaps the core area of our interest is condensed matter physics, so I will say a bit about the perspective from that point of view. Of course, the Muon USR technique, Muon spectroscopy can be viewed as a sort of branch of magnetic resonance. So there's clearly a perspective from the point of view of magnetic resonance in general. The Muon also behaves like a highly reactive hydrogen radical. So there's a sort of whole branch of muon chemistry which provides another contrasting perspective. And another perspective that's been coming to the fore recently is a computational science perspective. So one can actually work out in quite a bit of detail what the muon does in materials, and it's very, very helpful to getting the most out of your muon data to follow this direction. And then finally, the actual USR experiment, which is the thing we home in on to do our USR experiments. So what are the important things from the point of view of a USR experimentalist? So key properties of the Muon. Well, discovery was back in the 1930s, 1936. Carl David Anderson, Seth Nedemeyer working in California. Now they didn't have high energy particle accelerators in order to generate muons, so they had to use the natural muons in cosmic rays, and they used the recently discovered cloud chamber technique to study the cosmic rays. And in fact, Carl David Anderson received a Physics Nobel Prize exactly the same year for his discovery of antimatter, the positron, and they were using exactly the same sort of techniques for that. So what one had at that point was then this new particle, the muon, which is an unstable charged particle, but 200 times heavier than the electron. And it was not entirely clear how that fitted in with the perspective of matter at that time, which was a nucleus made up of protons and neutrons and electrons surrounding to make the atoms. And this muon seemed to not fit in very well. And so there was a famous quote by Isidore Rabi, who said, "Whoever ordered that?" It was a rather unexpected particle. He, of course, is quite important in the history of USR as the sort of founder of the NMR technique, for which he got a Nobel Physics Nobel Prize in 1944. So there was some initial confusion about how the muon fitted in with the elementary particles, whether it was an elementary particle or not. But eventually things settled down, and it became understood that the muon is actually a lepton, so it sits beside the electron and the Tor lepton, and a family of 6 leptons where you have the particle and its associated neutrino. So what are the sort of key properties of the muon in comparison with our more familiar particles, the electrons and protons that we see making up matter? So they're all spin half particles. You see the mass is somewhat intermediate between that of an electron and a proton. So it's 200 times heavier than an electron, but it's about 9 times lighter than a proton. And the magnetic moment is correspondingly scaling in the same way. We can have both positive and negative charges for the muon. We mostly use the positive charged variety. And so one can view this in terms of its mass and its charge as a sort of light proton. The negative muon has a rather short lifetime for various reasons that we'll discover in later talks. And it's best to view this as part of a heavy electron. So in terms of magnetic resonance techniques, of course, for electron we have ESR, and for protons and other nuclei we have NMR. So the term was coined USR to describe magnetic resonance type techniques using the muon. But actually the muon, we're generally not, I mean, sometimes we're doing resonance, but more often we're measuring relaxation or rotation. So this R can stand for many things. It's sort of in the eye of the user what that R stands for. You could just say it's muon spin research, which is a sort of actual term. So the key properties of muon are that it decays, producing a positron or electron in the case of a negative muon, plus 2 neutrinos. And it's these positrons that we detect to form the muon spectroscopy technique. This decay is a result of the weak nuclear force, and because it's weak, we get that there is a slow decay rate associated with it. So that's why we have this relatively long lifetime for an unstable particle. We also get asymmetric positron emission because of this weak nuclear force is parity violating. So these two things are very helpful, which allow us to use the muon technique. So what this means is that the parity violation means that the emission of the positron is preferential along the direction of the spin of the muon. So if you just look at the maximum positron energy, you have this sort of polar pattern where you have a very large emission along the spin direction and a small emission along the reverse direction. Now, in fact, you have a range of positron energies from this free body decay process. So when you average over all these energies, you then end up with something which is still asymmetric, but not quite so extreme. And your asymmetry parameters are of the order of a third in that case. So moving on to the high energy particle physics perspective, the cosmic rays, as I said, were the first sort of high energy particle accelerator before the purpose-built ones were available. And how these work is you have high energy protons and atomic nuclei that are mainly coming from outside the solar system. These are the primary cosmic rays. And when they get to the upper atmosphere, they hit the atoms in the atmosphere and produce showers of secondary particles, including muons. And the large number of these muons are what come down to reach the surface of the Earth. So this is what the measurements in the cloud chamber were looking at. And in fact, muons played quite a significant role in the early development of particle physics because they're so numerous in these cloud chamber measurements. Another interesting starring role for muons was in providing the first experimental proof of Einstein's relativistic time dilation. So the Rossian Hall experiment in 1941, they measured the muons up at the top of Echo Lake, sort of up a mountain in Colorado, and then compared that with Denver City down at 1,600 meters. And by looking at the different momentum ranges, they could see what the survival probability is between going from the high level to the low level. And they found a slower decay rate for the higher momentum muons, which fitted in very well by relativity. So this enhanced lifetime means that they survive, the higher energy muons survive longer. And in fact, their estimate of the muon lifetime was reasonably good, certainly consistent with our more accurate ones we have now. Continuing the high energy particle physics perspective to more modern times. So everyone will have heard of the Large Hadron Collider at CERN, and this is the main. These large instruments there are actually tracking muons as part of their purpose. So, for example, this compact muon solar, not very compact, but that's what they call it, and these play an important part in discovering the Higgs particle in recent years. So the muon tracks are shown in red here, and these are Higgs decay particles, the Higgs particle decay, and you infer what its properties are from tracking muons. So the muons are clearly playing an important role there. There are other high energy or other particle physics experiments that are also very current. So looking at the muon G-2 it actually turns out to be a very good way of testing the quantum electrodynamics theory and the standard model of particle physics. And there's currently a significant deviation between theory and experiment, so which can't be explained in terms of any of the new particles. So there are new experiments being planned, one in Fermilab, which is now taking data, and another one in JPARC is building up. So muons are very much at the forefront of particle physics currently. There's also future plans which are based on muons for high energy physics. So muon colliders is one idea, to go beyond the hadron colliders like CERN and use muon colliders. Another one is neutrino factories, So of course the muon is decaying into neutrinos. If you want to make a lot of neutrinos to study, you want to make large, intense muon beams. So plans for this sort of thing. And both of these things require storage of muons in storage rings. But of course, this is all focusing on high energy muons, and that's not really what we want. We want low energy muons. So what we have are typically 3.9 MeV muons. The typical muons we have are called surface muons. You'll hear more about the types of muon production in the next talk. So what we want to do is stop our muon beam, slow it down in a sample so we can actually study what's going on. So we want to stop and thermalize muons in the sample. Now, the state that the muons form in the sample can take several forms. And one important one is called muonium. And this is where a muon picks up an electron and forms a sort of analog of hydrogen atom. So you can then view the states in terms of, so the positive muon, the bare positive muon can be viewed as an ionized form of this muonium atom. But it's also, H minus is very stable. You can also have a mu minus state as well with 2 electrons. And this is called diamagnetic because there's no unpaired electron spin involved. The other type of states are referred to as paramagnetic, and in these you have an unpaired spin. So the normal muonium would be in that category, but the muonium can also react with chemical species to form muonium radicals, which would also fall into this class. So from the point of view of the radiation and physics chemistry perspective, one wants to sort of follow the slowing down process and understand a bit about what's going on there. So there's a sort of early stage process where the muons slow down by ionizing and exciting along their path, and you end up with radiolytic electrons and excited states along this path. Eventually, it comes down to a relatively low, down to the kilovolt, tens of kilovolts level, and you start to resolve a charge exchange cycle where you're forming muonium and then ionizing the muonium to go back to mu plus, and this sort of carries on capture and loss process as a way of losing further energy. But at some point, your energy comes below this energy difference of 13 eV, and you start to thermalize. And you can either thermalize with the electron, and then you have a paramagnetic muonium state, or you can thermalize without the electron, and you have a diamagnetic state. But you can also have various transitions between these states. So, for example, the chemical reaction I talked about, you could then form a muoniating radical, which is paramagnetic, but that could ionize, or you could have some of these radiolytic electrons could reach your diamagnetic, form muonium at a delayed state. So there's all sorts of possible paths for the radiation physics chemistry that find a slowing down process, which is quite hard to model. There's also possibility of hot reactions. But the key thing to note from this process is it occurs on a very short timescale, or the nanosecond, and it preserves this 100% muon polarization that one started off with, which is very helpful for us for the muon spectroscopy. So now moving on to the condensed matter physics perspective. So here we're taking our thermalized muons and using them as local probes of static and dynamic magnetism. So as far as static magnetism is concerned, so you typically have 2 cases. So one is the muon has a sort of limited number of well-defined sites. You can then analyze your data in terms of these specific sites. You can then tie it in with site calculations to aid this analysis and get a very specific answer about what's going on and where it's happening. Another type of situation is where you have the muon as a statistically sampling probe. Now, a classic case here would be a superconducting vortex lattice, where you've got a very long magnetic length scale compared to the unit cell of the underlying system. So the site itself doesn't really matter so much as the distribution of sites within this magnetic length scale. And another situation where you have this sort of statistical sampling, if you have a very large cell combined with many oscilloscopic sites within the cell. Also, if you have a very high degree of disorder, then you can't really talk about individual sites so much. You have to start talking about distributions. And then finally, the quantum properties of muon can lead to delocalization, which again gives you something which is sampling across the lattice. So switching over to dynamics, what's our sensitivity to dynamics? Well, it depends on two things mainly. The strength of the magnetic coupling to the muon, which we call A, is a generic hyperfine coupling, triple dipole, we call it A. And the characteristics of the muon source, so it could be pulsed or it could be continuous. And the thing about pulsed source is that you can actually measure relatively low relaxation rates. You struggle more with the fast relaxation rate. And the converse with the continuous source is they're good at measuring fast relaxation rates, but the slow relaxation rates are harder. So then, depending on this coupling, you have a sort of different regions of sensitivity. So, for example, if you have a relatively low coupling value, as might be typical for coupling to nuclear magnetism, say 0.2 megahertz, then the ability to measure low relaxations of the pulse source gives you a nice wide range of sensitivity. Now, there's two colours here, there are two regimes basically, a slow fluctuation regime where you measure directly the fluctuations, and then a fast fluctuation regime where you indirectly measure the fluctuations. There's a sort of motional narrowing effect. And that is very much dependent on the value of A, whereas the direct method is independent of A, apart from the fact that it crosses over between two regimes. So for the faster case, the ability to measure slow relaxation. So if you've got a strong coupling, you get a large range, but you get rather a hole in the middle with the continuous with the pulse source. Whereas the continuous source, you have a more smooth region. But on the other hand, for the slow fluctuations, you have a more broad continuous regime compared to the continuous source. The pulse source is better. So each source has its own strengths and weaknesses. So we have a sort of broad range for what USR dynamics we can be sensitive to in terms of correlation time fluctuation rate. And see, this is sort of graph showing how it fits in the spectrum of different measurements you might use. So, for example, static magnetic measurements measuring resonance are very slow techniques. We can move up to switching to AC susceptibility to move up the fluctuation rate range, and that sort of overlaps with NMR. And then on the fast end of things, you have neutrons, you have Mossbauer, which works for certain systems. But USR straddles rather nicely between the NMR and sort of neutron regime, so it has a good place. So in regions where things are too fast for NMR or too slow for neutrons, then the USR is particularly well placed. So one of the things that is useful to study in the condensed matter perspective is ionic motion and dynamics of ionic motion. So, for example, if you have several equilibrium sites in a system, such as copper, you could look at diffusion in copper, actually motion between these sites, and this can be studied with USR. And of course, in more complex materials, such as lithium battery materials, which are very technologically important, you can also do similar things, studying diffusion rates and so on, the function of composition. So, sort of broadly summarise some of the benefits of USR versus magnetic bulk magnetic studies. So there's some interesting things here. In the Muon is a volume average probe. So often if you're doing bulk magnetic measurements, you're actually very sensitive at low temperatures to rather low concentrations of impurities, which kind of mask what's going on intrinsically. But you don't have this problem with muons because you just average what's going on in the bulk. And the weighting of impurity phases matches their concentration. And you can also tell the difference between phase segregated and uniform samples for the same sort of reason. Another particularly good strength of USR is it's very sensitive to antiferromagnetism, which is more difficult with the bulk methods. And of course, we have the possibility of measuring in zero applied field. So this is useful for systems that may be very delicate and could be perturbed by actual applied fields in the measurement. Some other key features of the USR technique are its high sensitivity, the fact you can actually detect very small moments, fractions of a 4 magnetron, which is very useful, for example, when searching for time versus symmetry breaking superconductors as well as one application. And as I said, there's no need to apply an external magnetic field, so that can all be helpful. And in fact, when you're doing zero field studies, there's no need to apply an array of sample, which also can be very helpful. And finally, we have a very good compatibility with low temperatures, because both our incoming muon and outgoing positrons can easily penetrate the walls and windows of the cryostats, so it's It makes it a very good technique for low temperature. So as I'm switching to the magnetic resonance perspective, so as I mentioned, we have USR as something that we can compare with ESR and NMR, and we can really view USR as being a sort of more sensitive version of proton NMR. So what are the advantages of USR over NMR? So we have this 100% spin polarization from Muon, which is a great benefit, whereas we have a very weak polarization in general for NMR nuclei. We have this large gyromagnetic ratio that's larger than any nucleus, so we have convenient frequency. We have no need for any specific nuclear isotopes. We can implant muons in anything. And we have this quite a full range of field developed for measurements. It's very easy to change the field in USR. It's not so straightforward in many magnetic resonance techniques. So we can go from zero field, and with the right instrument, we can go up to 10 Tesla or so. And relatively easy sample and set up, provided you have access to a muon source. And as I said, we're compatible with low temperature sample environments, such as helium dilution fridges. And as I mentioned before, this wide range of correlation times we have potentially access to, which is kind of the benefit. So of course, there are some disadvantages of USR compared to NMR. Admit this. So we have this muon lifetime. We need the lifetime to actually do the technique, but it does limit our potential for spin manipulation by using RF methods. And we need to look, understand the muon stopping sites to fully interpret our data. So that's something. NMR, you know where your spin probes are. We don't necessarily. There will be some perturbation of the system under study by the Francis Muon. That's also something that has to be considered. And compared to NMR, larger sample masses would typically be needed in USR. Okay, so moving on to the chemistry perspective. So we have the hydrogen atom as the simplest possible free radical, which is highly reactive. So if we look at muonium in this terms as being a radioactively light isotope of hydrogen. So one can then study muonium in terms of following the chemical reactions of the hydrogen-like species. So what happens is typically in a system, you have a double bond in a system, and then the muonium will add to this double bond. You will end up with a delocalized, unpaired electron, and then the muon will couple to this electron, but you also have to take into account coupling of the protons to this electron in the system. So that's a relatively small system. If you take a sort of larger system to understand how the delocalization works, so this is an example of benzene, so muon adding to the carbon site in benzene. This will be the spin density. So the muons here, you get the spin density, and you notice this alternation in sign. So you get a negative spin density here, and a positive spin density, a large positive spin density here. So you get this sort of alternating pattern of spin on the carbons. The spin on the muon and the hydrogens, it sort of follows, but in the opposite sign as well. So it sort of matches the pattern you see in the carbons. But of course, unless you've got carbon-13, the important spin systems for coupling are the protons and the muon. But having this spin distribution will affect the muon, because you'll have a dipolar coupling to the spin distribution, even if you don't have a hydrophile coupling. So understanding the distribution on the molecule is an important part. So, as I say, we have an isotopic species here with the muonium. So you can think of it extending what you already have with deuterium and hydrogen. You now have an even lighter species that you can add to that sequence. But one of the points having this light species is you have a very large quantum fluctuation, 0-point energy. So if you're sitting in a potential here, whereas the deuterium, the proton will be down near the classical minimum, the muon will be well up the potential. And in fact, you can use this to test your interatomic potentials and theories of chemical reaction and so on. And actually, with a laser, you can take it even higher up to the first excited state, which would be like 3 times higher up, about 1.5 eV from muon. So you really do have potential to study these potential energy surfaces. So the spectroscopic study of these Muon interferometric fields gives information about molecular spin distribution, molecular environment, molecular dynamics, a range of things. And it's a technique that will be described in detail later. It's called the voided level crossing. But just sort of show some sample data, sort of how it works. So this is a polyaromatic hydrocarbon called corannuline. And if you look at this system, it's a sort of like a sort of baseball cap type arrangement. And there are about 4 different sites where the muon can add. So if you do the spectroscopy, you can then identify these 4 different sites. Each one has a different line pathway. And then if you change the temperature, you can see that the line shapes are changing. So it's responding to the dynamics in a way that you can study. So this is a sort of typical spectroscopic study of one might make. Okay, so as I mentioned, there should also be a computational science perspective. So from the point of view of the muon, from a computational scientist perspective, it's really a sort of hydrogen interstitial defect problem one has here. So for example, you can use computational methods such as density functional theory to calculate the structure of such a defect. And an important point is that you will actually distort the positions of surrounding atoms, not just the local ones. So there will be a distortion pattern that one has to calculate. And the techniques are coming along nicely to be able to do this sort of thing in a range of problems. But there is, of course, an extra challenge in computational science because of this strong quantum character of the muon that I was mentioning. So when you do a standard computational method such as density functional theory, you're getting the classical minimum of the potential. For most atoms, this is okay, but proton that you start to worry about quantum motion, that the muon is very much stronger. It's like so it's like protons on steroids. You have to take this into account if you're going to do a proper calculation. So that's something that's being developed. Okay, so my last main perspective is the USR Experiment Perspective. So here, what we're usually working with when we come to do a muon experiment is we have a muon spectrometer to do the measurements. So what is a muon spectrometer? Well, it's an array of positron detectors basically placed around the sample to detect this asymmetry pattern. And they detect positrons and the asymmetry emission. So, for example, you have a forward detector placed in the initial spin direction and a backward detector. So, if you apply a transverse field into the screen here, this whole pattern will process round, and the higher positron emission direction will then change and will go around processing. So you then look at the 2 detector signals. You have your forward detector, backward detector, and you see this oscillatory behaviour. And the amplitude of the oscillations will reflect this A parameter. But you see, of course, it's superimposed on the exponential decay of the muons as a pattern. So these detector signals can be described in mathematical form. So you have this exponential decay as one term, and then you have this 1 plus asymmetry term, which in this case is oscillatory. So this is the oscillatory polarization function. So in this transverse case, it can be described as a cosine function and then a transverse relaxation function. Now this transverse configuration is not the only one we use. Quite often we're using a simpler configuration, which is longitudinal zero field configuration. So here we only really, here we have the applied field along the direction of the muon spin, whereas the configuration I was looking at before has the field perpendicular. So actually, the definition of forward and backward detectors is a slightly confusing thing in USR, because in my case, I'm defining them logically in terms of where the initial spin direction is. But of course, the initial spin direction can be affected by moving your spectrometer around with respect to the muons, or using a spin rotator, which is a device which will rotate the spin. So it can be a bit confusing. And instruments are often define their detector names in terms of their physical beam geometry. So just, is it are you forward or upstream or downstream of the beam and so on. But I think it's better to define these forward backward detectors in logical terms. And in fact, you often grouping detectors together to form these logical detectors. So this is particularly with pulse sources, is a good way to think about it rather than physical position in space. So it's convenient. Often we have this exponential decay. It's often convenient to normalize that out, so we can just focus on the polarization function. And the standard way of doing that is to take your pair of detectors, you forward and backward, and then you just take the difference, and then you normalize by the sum, and that has the effect of normalizing out the exponential decay and just giving you the polarization function. You often have to use this so-called alpha parameter, which is a calibration factor, which allows for any difference between the forward and backward detectors. So in USR, you often, first thing you do is do this calibration. So when you do that, you get a nice polarization function here. So if you're in TF mode like this data here, this asymmetry normalized by the initial asymmetry then gives you this transverse relaxation function that I mentioned and the cosine describing the oscillatory path. Now in the zero field, longitudinal field mode, we generally just take the normalized asymmetry to be the longitudinal relaxation function. So you will often have oscillations in zero field mode, which would be due to internal fields in the sample, but they are treated as part of the relaxation function. There's slight difference between TF mode and LF mode. But anyway, the key point here is that what we're doing with spectroscopy is we measure this asymmetry as a function of time, and what we are doing are analysing this asymmetry in terms of these relaxation functions, like the transverse or longitudinal field, and that in a nutshell is what we're trying to do with spectroscopy. So, to summarise, we're up in time. So we have the muons, and it's historically starting off in particle physics, and a very rich history, and continued current relevance. So there's a sort of parallel interest in muons at the high energy physics end of things, which may be useful for shared interest in generating high intensity muon sources, for example. Muons can be easily plugged in tails to provide a local spin probe, so this is certainly the case. And there's an extremely wide range of applications for muon spectroscopy. I just didn't cover them, but you'll hear about all sorts of things in the coming lectures over the week. There are many advantages of muons over other experimental techniques, and a few disadvantages in various places, but we'll focus on the advantages. It's relatively easy to obtain USR data on our samples of interest, but data analysis and interpretation often needs a range of knowledge and skills to do properly. And really, this school, the purpose of that is to help with this process of getting a good range of knowledge and skills to do USR experiments and make the most of USR data. So finally, I'll just come back to Isidore Rabi for some nice last words. Actually, it's Isidore Rabi's mother whose words she would ask him, did you ask a good question today? Which I think is a very good question for all scientists and in particular muon spectroscopists. So with that, I'll leave you.